Hi there, welcome. This video is to talk about Bernoulli's principle and fluid flow. So there's another video with Pascal and Archimedes, the first two parts of the fluid chapter, Pascal and Archimedes, dealing with pressure and buoyancy. This piece is really about Bernoulli, fluid dynamics, moving fluids. And what do we know about moving fluids? The faster a fluid moves, the lower the pressure. So as a speed or velocity of a fluid increases, pressure decreases. This is how we get lift. So if Archimedes' principle deals more with buoyancy, why a ship can float, Bernoulli's principle deals with things like why a plane can fly. So if I had my piece of paper, clearly I could try to make the paper fly by pushing underneath it, but watch what happens when I blow across the top. By blowing across the top, as the velocity increases over the top, the pressure decreases. The high pressure underneath lifts the paper up. So Bernoulli's principle is that as the velocity of a fluid increases, pressure decreases. Now, what are some applications? We're going to be dealing with things like maybe a water pipe, or in this image, a sprinkler system. So in my sprinkler, and this is not drawn to scale, I've got a 3-centimeter diameter pipe that's going to narrow a little bit and go up. And eventually the water is going to shoot out. And the question would be, as the water shoots out, a couple of questions. One, well, if the velocity is moving 2 meters per second down here, how fast is it moving when it leaves the pipe at B? So that might be one question. How fast is the water moving at B, given that it's moving at 2 meters per second at point A? Okay. The second question would be, what's the pressure down at point A where the water's actually moving slower? We're going to find out that the water's moving faster at point B. We'll solve that in just a second. But then how much greater is the pressure at A? Because I know that as the velocity slows down, pressure increases the same way as the velocity speeds up, pressure decreases. You might see this in terms of a pipe that moves kind of like this on an FRQ question. And as that pipe kind of narrows or goes up or down, the fluid goes from here to here to here. You know what happens is that pipe kind of bends and moves to the velocity and the pressure at the different points. Well, pressure matters with depth. We see that in Pascal, and there's another video for that, Pascal and Archimedes. We also know that pressure is affected by how fast the fluid's moving. So let's deal with that. So first off, in this kind of hypothetical sprinkler, as my pipe narrows, how fast is the water moving at B, given that it's moving 2 meters per second at point A? Okay. Well, the cool thing about liquids as a fluid, liquids are mostly incompressible, meaning if the pipe starts to get smaller, the fluid has to speed up. Why? Because it can't really bottle up too much. It has to speed up. If you've ever put your thumb over the end of a hose, you'll notice that when you put your thumb over the end of the hose, if you cut the cross-sectional area in half, the velocity of the water has to double. It has to, because the same volume of water has to pass a point every second. We see that in rivers. If a river is wide and deep, it runs a bit slower. But as that river narrows or goes through rapids, the cross-sectional area gets smaller, the water has to speed up because the water is mostly incompressible. So we have this thing called the continuity equation. The continuity equation says, hey, look, if you know the cross-sectional area of your pipe, the cross-sectional area, like how big is this pi r squared, and I know the velocity, the product of the cross-sectional area and the velocity has to be the same everywhere. So if the cross-sectional area is getting smaller, the velocity is getting bigger. Okay, well, let's apply that to this problem. I know that area is pi r squared for a circular pipe, and velocity is going to be v. So I'm going to look at the pi r squared at A versus the velocity at A and compare that to pi r squared at B and the velocity at B. Okay, so pi, well, let me be a little bit careful here. If the diameter at A is 3 centimeters, we'll get a different number, 3 centimeters. The radius is 1.5 centimeters, but centi is 2 to the left to get to meters. We always deal with meters in physics. So 1.5 centimeters would be 1, 2. Okay, so 0.015 squared. So if the diameter is 3 centimeters, the radius is 1.5 centimeters, and then I have to move the decimal twice to get 0.015 meters. Okay, so pi r squared, that's the cross-sectional area of my pipe. And then the velocity is 2 at A. Well, I can set that equal to over there at B. At B, now I gotta be a little careful again. At B, the diameter is only 1 centimeter. That's pretty small. So the radius is 0.5 centimeters. But again, we like to deal with meters in physics. So that 0.5 is going to go 1, 2 to the left, 0.005. 1 centimeters, 0.5 centimeters, 1, 2, 0.005. Okay. All right. So there's my equation to find the velocity at point B. And what you're going to notice is that pi will go away. And when I divide the left side by the 0.005 squared, I end up with a velocity at B of 18 meters per second. What's happened is, as the pipe got narrower, the velocity had to speed up. And in fact, there's a bit of a ratio here. If the diameter is 1/3, because of the pi r squared piece, the radius is 1/3, but pi r squared means the area is only 1/9, so the velocity is 9 times greater. So I find the velocity at point B is 9 times greater, and I can use the continuity equation to find the velocity. So on a free response question on the test, if you knew the velocity, say at this point, and if you know the diameters at different points, you can find the velocity at point B or velocity at point C simply using velocity A1 V1 equals A2 V2. I can use the area at this point and the area at this point to find the velocity at B. I can use the area at this point and the area at this point to find the velocity at C. So this would be a good free response question to find the velocity at different points in the pipe as the diameter changes, cross-sectional area changes. Now, what do I do with that in terms of pressure? Well, because the velocity is greater at B, we just found the velocity up here is 18 meters per second. That means that's the place where the pressure is going to be less. In fact, the pressure should be greater down there at point A for 2 reasons. One, the fluid's moving slower at point A, but also it's deeper. I know that pressure increases with depth, but also pressure is going to be greatest where the velocity is least. And I just found the velocity is much greater up here. So how do I find the pressure at A? Well, Bernoulli's equation is quite long. What in the world? The pressure at A plus rho GH. Now, what is rho? Rho is the density of the fluid. So for us, our density is going to be 1,000 kilograms per meter cubed. And that's also discussed in the pressure video. G is 9.81 meters per second squared. That's the acceleration due to gravity we've dealt with all year. V is velocity. So how could I apply this? What does this mean? This means the total pressure, total pressure at A has to equal the total pressure at B. And that pressure takes different forms. There's the absolute pressure. There's the pressure with depth, H. There's the dynamic pressure, 1/2 rho V squared, the moving pressure. It looks like a kind of a crazy equation, but in some ways it's simple because it looks just like our energy equation. Remember potential energy, mgh, kinetic energy, 1/2 mv squared? It looks very much like our conservation of energy, meaning the total energy at one point equals the total energy at another. Or in this case, the total pressure at one point equals the total pressure at another. So let's go ahead and solve this and kind of be done with this piece. The pressure at A is what I'm looking for. Now, rho GH is interesting because that H, that height in rho GH, has to have a frame of reference. Well, guess what? I can make one of my heights 0 as long as my other height is consistent with that. So I could say, hey, look, the height at A is actually 0. Perfect. No problem. So plus 1,000, that's the density, 9.81 times 0 for my height, plus 1/2 times 1,000, that's the density of water, times the velocity. So there's the left side of my equation. I want to get the pressure at A, given this whole term is 0, and the dynamic pressure is 1/2 times 1,000 times 2 squared. But I've got to set that equal to something. Pressure at B. Okay. Well, what in the world is the pressure at B? Well, here's the thing. We found out from the Pascal piece that whenever we're open to the air at sea level or ground level, atmospheric pressure there is 100,000 pascals. All that atmospheric pressure is 100,000 pascals. So because B is open to the air, the pressure there is going to be 100,000 pascals. It's going to be atmospheric pressure. So back down to here, and feel free to pause the video or go back. This is 100,000 pascals, about 14.6 or 7 pounds per square inch is what we're used to our atmospheric pressure being. Plus, okay, rho GH here. So now my height is not going to be 0. My height is 1.5 meters above the other height. Why? That little piece is given in the problem. The top of the pipe is about 1.5 meters above the point A. Okay, so then to finish this off, and I hope that my velocity is good because that air is going to carry forward here, but I got about 18 meters per second. So there's my big long equation. This is Bernoulli's equation that says the pressure at A plus rho GH at A plus 1/2 rho V squared at A equals the pressure at B, it's open to the air, plus 1/2 rho V squared, or rho GH rather, plus 1/2 rho V squared at B. The left and the right side should equal. So all I have to do is add all of this, squared, subtract that, because that's 0. And my pressure at A, I get, you can double check the math, around 274, 715. And that kind of makes sense to me because the pressure is quite a bit more than the 100,000 pascals of atmospheric pressure at ground level. I would expect the pressure to be greater for 2 reasons. One, the fluid's moving slower. If faster means lower pressure, slower means higher pressure, but also I'm deeper there. The deeper you go into water, the more the pressure is. We see that when we dive down into the pool and the pressure gets greater and greater. So that's how to solve that. Now, what you might see on the test again is some kind of curvy pipe that looks something like this. The first move to do, if this is A, point A, B, and C, if you have to find, say you get the velocity at A is 3 and the diameter is 4 and the pressure is 200,000 pascals. You might be asked then with that information to find the velocity at B or the pressure at B, the velocity at C or the pressure at C. Well, all you have to do is equate the information at A to either B or C. Be a little careful. There would have to be some heights given. One of your heights can be 0 as long as your other height makes sense. And then, you might have a height over here at C. And so I have to kind of reference that. But that way I can solve for B or C given the information at A using this equation. And that equation would be certainly given on the data sheet for this test. For the data sheet for this test, you would get this equation, the continuity equation, those would both be given, as well as densities like 1,000 kilograms per meter cubed for water. The pressure at sea level, 100,000, in case you needed the pressure at open to air at sea level. The acceleration due to gravity, 9.81, all those constants that we used, those would all be given. Okay, so that's how to solve Bernoulli. That's how to deal with the continuity equation in Bernoulli. Definitely check out the video for Pascal and Archimedes, and I hope this helps. Take care.